It's like a picture of a little girl cutting herself.
That's what it looks like on the package.
I've seen that.
She has red eyes. And that's what it looks like under the foil.
Like I literally saw it, and
I know. And you push the button, it's this really evil.
Yeah, and it has like an evil voice that comes out.
What?
Yeah.
What?
I don't know.
Of course, they named it the evil stick. So I mean, I don't know if I would buy that for my daughter.
Yeah.
It looks nice, but it's called the evil stick. Oh well, here, go play.
I don't know. I think regardless it's sick because if for parents that don't speak English and they just go buy it, you would never in your mind think that your child's
Especially if they just put it right next to normal princess stuff.
No, yeah, it's all
Right?
like fun and
It looks like a
normal.
princess little wand thing or whatever. All right, guys. So let's try this out. Let's see. All right. I think several of us, for one thing, are not really trying the homework out. I don't know what's going on there. We need to really try this out. And the way to do these problems is to completely separate. That's why I try to make it A, B, C. Each part of this by itself is remarkably easy if you let it. I think most of you guys just have the whole thing in your head at once, which actually is true about all of mathematics. If you're able to break a problem up into its parts, if you're able to do that naturally, you will do much better in math. If you're not, you need to start realizing it and start doing it. So the very first thing I'm worried about, the very, very first thing I'm worried about is just what the hell is the claim? And the claim will almost always be something like, we believe that, it is thought that, we think, those kind of things. That's going to be exactly what the claim is. So in this case, I use the language, we believe that the average has increased. So in this case, I'm talking about averages, so what symbol do I want to use?
Mean.
Mu. And we think it's increased from what it used to be. So how do I write that?
Greater than.
Greater than? 24.81. So we think the average has gone up from what it used to be.
So if it was decreased, it'd be less than?
Yeah, exactly.
Okay.
That's all. If we think it's increased, then what do we think it is? Is it's bigger than what it used to be?
Right.
Yeah. If we thought it had changed, if we say we think it's changed,
Greater than.
Doesn't go either or.
does not equal to. Yeah. The only way it can change is if you're not equal. How can you change? You can either lose weight or gain weight. You can either have a grade go up, have a grade go down. So you got two directions you can go. That would be when it's a two-tailed test. The claim is we think it's different. We think it's changed. Even this is the most evil one. We believe that it is this. And everybody pretty much misses that. But is, of course, is the code word for equals. So that would be where the HO happens to be the claim. It's equal to. That would be still a two-tailed test, because what's the opposite of equal to? Not equal to. Crazy. So I want you to realize the first thing you worry about is what the claim is, and the last thing you worry about is what the claim is. In the middle, you don't give a shit anymore. I think that's also creeping in your head. You try to connect claim with HOH. But no, just look at what I've written so far. Which one does that have to go into? Why does it have to go to H1? There's no equal sign. There's no bar. There's no equals. There's no bar there. It doesn't have any equality to it, so it must be H1. So I just put it directly into H1. And then whatever's blank is going to be the opposite of that, because it must be the opposite standpoint, right? So what's this guy going to be?
Mu is less than or equal to.
Kick ass. So this one, no matter what, I don't care what the claim is anymore right now. I'm getting into the problem now. I don't care what the claim is anymore. H1 always sets up the rejection region. Always. So it tells me exactly how many tails and where it's going to peak, because there's a greater than symbol there, right? It points in the direction of your tail. So if it's a not equal to, it's actually like pointing both directions. So in this case, how many tail tests? One. On what side? The right side, greater than. It's pointing up. So it's going to be a one-tail test. It's going to look like that. Or maybe even better than that. Okay. So that's part A. So the very first thing you worry about is what the claim is. You write that statement down, and then you forget that it's a claim. You just look at it. It's a math statement. Where does it go? No equal sign H1. Equal sign HO. Whoever's blank must be the opposite, because these two guys, they think opposite about things. Yeah.
If you said we believe the average has changed or is different or whatever, and it's a two-tailed test, would the claim be the hoe then?
Well, it depends. If you said different,
Yeah,
then the claim would be not equal to.
because it's equal.
That would be H1. Because
Okay,
what's the opposite of not equal to?
equal to.
And that's definitely going to be HO.
Okay. Yeah.
Not equal to is the most not equal containing thing, because it. Do you know what I'm saying? I mean, oh, come on now. So obviously, if I have this, is there an equal sign there? Yeah. So which one would it be? HO. If I have this,
It is high.
that would be H1, right? And then as soon as I write that down, I can figure out what the other one is. It'll be the opposite of that. Now, if I say I think it's not equal to,
Yeah.
that is not equal. That's the not equal sign. You can't be any more not having an equal sign than the exact opposite of an equal sign, right? You guys with me?
Yeah.
I really want you to see. It is kind of silly, but that's how simple it is. Because what's the opposite of this?
Equal.
It's going to have the direct equal sign. So the opposite of this must be the HO, right?
Okay.
So you know this has got to be H1. It doesn't have an equal sign. It's got the exact opposite of an equal sign. Don't make that an issue. But I like to say, well, behind the thing, there's an equal. No. That is the not equal to sign. That is so desperately not an equal sign. It is. All right. So then HO here would be U equals 29. Now I know I'm right. If I would have put that there and put the opposite, I should go, holy shit, I got the equal sign in the wrong place. All right, just switch them. You haven't turned the damn thing in yet, so you can still switch them. Okay. So it's not hard to make more of this than it is, because it is not a little bit of something, but it's not as much as some of you guys think it is. I think you try and it's not hard to do that. So let's see, part B is always the same thing. And what are you always looking for in part B? If I'm talking about means, what two things do I have to be able to say? Yeah, I got to say it's normal somehow. So that would be one. Either they say it's normal, or the sample size is big enough.
Yeah.
And then, so that's number one. So is that true? Yes. They don't say it's normal, but we do have a sample size of 264, which is bigger than
30.
30. Check. Central limit theorem. Yay. So that, what I've written so far just means I can do something. You can't say, forget this, Jeff, and move on. At least if you want to make a good grade. Now I want to know, which one do I use, Z or T? Why were T-scores invented?
To cover up the sample deviation.
When we only know the sample, to cover our ass for when we don't know the population standard deviation, when we only have an estimate. Any sample standard deviation is probably going to be wrong. So if I want to use a sample standard deviation, it's going to be an estimate. So T-scores kind of cover me for that. They make everything a little bit bigger. They make the test a little bit harder to pass, to make things more conservative, because there's something I don't know. In this problem, do I know sigma? Yes. Yes. I tell you directly. In fact, I have to be pretty much this direct when it's a population. I told you that way long time ago, because our base reaction normally is it's going to be a sample. That's what we normally use. But this is a population standard deviation. I'm going to tell you directly. Or I might say the standard deviation for all women is having the age of the first birthday is this. That would be the population, that word all, right? So 1, it's normal enough. 2, sigma known, so I can use z-scores. So do I need to worry about degrees of freedom? Hell no. It's only if I have to use t-scores. So now I want to use, so now I know alpha is 0.01. I know I have a one-tailed test. And that's all I have to know to figure out what my critical score is going to be, right, for a z-score. So then if I look, this thing is set up beautifully for this. So I know it's a one-tailed test, so I'm only going to pay attention to this first row. I know alpha is 0.01. Bam. And I know I want to use a z-score, so I'm going to go down and not stop. So I get 2.326 for that. Okay.
That's good.
All right. So 2.326, and I know the tail already is going to be up here. So 2.326. If it was down here, it would be negative 2.326. The T-score chart has no negatives because they don't need it. We're supposed to be the humans. We put the negatives in when we want to, when we need to. How do you say this in words?
If G star is greater than.
Is
Greater than.
Greater than.
Reject. Null. Accept alternative.
You never accept anything. I know some of you guys know, and trust me, I'm not a wordsmith or anything. I'm not. That's one reason why I'm not an English teacher. It's also because my grammar's horrible, but it would never take me. But in this case, the language is really important. I can never accept, and I can never fully prove anything. There's always that little bit of doubt. In this case, I'll have a 1% chance of making a certain kind of mistake because we set alpha to be 0.01. So 1% chance that I'm going to reject a null when I shouldn't have. But that's a chance I can live with. 1%, that's really good, right? I'm not normally that small of a chance to be wrong. So that's how we say it works, and visually. So now that I've set up what's far enough away, what's enough evidence for a sample to show, I go see what the sample shows me. What do we know from the sample? What's X bar?
25.19.
25.19. What's X?
We have sigma.
Sigma. That's even better.
We've got 2.85.
I like that. I just want to see somebody pick up and you get it. So what do I have to do before I can get a z-score? What do I have to do?
Change it to sample standard deviation.
Good. So it's going to be the old one divided by square root of n. You do that no matter what. You got S, you got sigma, you do this. Because it's a question about standard deviation for groups, which is what this guy makes, versus standard deviation for individuals, which would not do me any good in this problem here. Right? So I always have to do this. So that'll be 2.85 divided by square root of who?
264.
264.
0.175.
0.175? Kick-ass. All right. So now I can make a z-score, and the z-score formula never changes. I know some of you guys don't believe me, and that's fine. But it's always our data. What's our data? 25.19 is what we found. Minus the middle, which we accept to be 24.81. Divided by the correct standard deviation, which now is 0.175. Some of you guys do this in here. That's beautiful. Just don't divide by square root of n twice. Right? That's a mistake I see some people make. And then when you do this, what you should get 2.17, right? 2.166?
Yeah.
So 2.17. We still round that to two places because I'm going to want to look that up on the z-score chart to get the p-value. So did we succeed?
No.
No. Yeah, we're down here, aren't we? We're at 2.17. That sucks. Well, it totally depends on how you feel about this. I don't have major feelings about this. I can't have a baby, thank God. If men had babies, there'd be a lot less people. So this is my z-star. From z-star, I know already that how would I say the results very quickly? What have we done?
Failed to reject.
We failed. So we failed to reject HO. Failed to support H1. So I can't say that the guy's wrong. I can't say the other guy looks to be right. I just haven't found enough evidence to say that. At least not at this level of significance. Now, how the hell do I find the p-value? Yeah, the area in the tail. So alpha is the area in the tail of the critical z-score. The p-value is the area of the tail of my z-score. So how do you find the area that's in this, that's above 2.17?
Look it up.
Yeah, you look up 2.17. Borrow somebody's test here. You look up 2.17. 2.17, I get 0.9850. most part. It's like, oh, not too bad. That's old news. Easy stuff. So don't make a big deal of p-values. Whatever z-score you calculate, the p-value is going to be area in the tail. The only time it changes is if it's a two-tail test, in which case you just double it. Now, we found the right number yet?
Nope.
Yeah, we got this area, 0.9850. So what's the p-value? 1 minus that. So the p-value is 0.015. I like it. So the other way, so I can compare z-scores directly. That z-score was not big enough. It did not get out far enough, so I failed. The p-value, is it smaller than alpha? No, which relates visually, my tail is bigger than this guy's tail. Right? Take that as you will. But so that's exactly the same thing as saying p-value is not smaller than alpha. Since this is further back, it's going to have more stuff in it. Right? So the p-value is bigger than that. But I know the p-value looks really not horrible. It looks pretty decent. What would it have done at 0.05 level significance? Would I have failed, or would I have been able to reject the null?
Reject the null.
I would have been able to reject it because it's smaller than 0.05.
Wait.
So let's look at that a different way. That's the next question. Since we're talking about p-values, I want to show you that real quick. The one other reason we get this, and like I told you, that's the only thing they're going to give in journals, like when they do an analysis. They're going to give p-values everywhere so that you can make up your own mind. So that's not going to be strong enough for some people. So the way I did the test at first was to have alpha at 0.01. So somebody's like, you got to really, really show me before I believe it. So that's not good enough. But if I was somebody with 0.05, right, then the most direct way to see it is my p-value smaller than that? Is the p-value smaller than 0.05? Yeah, 0.015 is smaller than 0.05. I would have succeeded. I would have found enough evidence. I would have rejected the null if it would have been 0.05. Right? That's an easier test to pass. Let's look at it a different way.
So it's just increasing the area that allows you to reject.
Exactly. So for 0.01, I had just 0.01 out here, and that made my z-score 2.326, right?
Mm-hmm.
Yeah.
So that was difficult to get, and we didn't get there. If it would have been 0.05, what would the z-score have been?
It would have been lower.
Yeah, it would have been lower.
1.645.
So one tail, 0.05, all the way down, 1.645. So in this case, we're at 2.17. Would we have succeeded?
Yes.
Yes. So that's the, I really want you guys to understand, that's why journal articles don't even go there. They're like, you can have your own level of significance. We don't care. Here's what we found. They would just report 0.015 and say, you guys make up your own damn mind. If you're somebody that, no, it's not good enough evidence, okay. If you're somebody else like this, holy crap, yeah, that's pretty good. All right. It totally depends on your own requirements. Right? Okay. So is everybody decent up to here at least?
Yeah.
2.17. Then you can compare that. The p-value thing, I really don't want that to be a huge issue. It's just looking up on the z-score chart. If it's a two-tail test, you got to double it to make it fair. But now what do we say here? What's my conclusion to this test here? To this test here. Did we make it inside? No. So we have
Failed.
not found sufficient evidence. So do what? Now I care about what the claim is. At the very, very beginning, it gets me started, and at the very end, it's how I word what I'm trying to say. So is the claim HO or is it H1? Yeah, in this case, it's H1. It's not always H1. In this case, it was. So then I want to use this not exact, but this wording here. We have not found sufficient evidence to support the claim that
The average child size is increased.
Yeah, that the average age, you can just steal the words directly from what I said. The average age at time of birth has increased. So we have not found sufficient evidence to support the claim that the average age at the time of the birth has increased. Right, we're just saying what the claim was. So we have not found sufficient evidence to support this claim. And you just go back and just steal the words directly. Just take the words about what the claim is. Just don't say right there to support H1. It's not good enough. Right? Tell me physically what the hell's going on in the problem. What is it really related to? And of course, the way to answer this question is, if we had used this, then our 0.015 is greater than, is smaller than 0.05. Fail. Get out of there, Jeff. This would have succeeded, yeah. Reject the null. Support the high. Because if we would have used the 0.05, it would have made it easier to pass. The tail getting bigger would have pushed the z-score down a little bit further, like you said. The z-score would have been less. So if you want to, you can always, for that kind of question, you know I'm going to ask that kind of question on the test. So for that kind of question, if you want to, you can just kind of redraw this and put 1.9645, is that what we figured out? Mm-hmm. So then our 2.17 would have been in the rejection region. We would have rejected the null, supported the H1. 0.015. Oh, that's the p-value. Yeah. So the two most important findings from our analysis is this 2.17. And if you think about it, some of you guys might be like, well, why do I have to go there? Because right there I know I can answer the question. Because again, I keep telling you, this is all that's reported to you normally for like a quick rundown of the results. So then you can make up your own mind about what it means. And this number is a little bit better because it tells me how truly strong it is. It would have passed, so the p-value's got to be less than alpha, so it did not pass 0.01, but it would pass 0.016, right? It tells you exactly how strong of a test it would pass. A z-score by itself can't do that for you. Okay, so if you're considering doing chapter 9, since that's extra credit now, and keep that kind of thing to yourself, yeah?
What is chapter 9?
That's what I'm going to talk about right now. No, that would be really mean to me.
Make it extra credit, you have to know it.
You don't have to do it, but you got to know it. Just lay the hands on there and you'll absorb it. So very, very quickly. From chapter 8, the z-score has just one sample in it, right? So in reality, I normally don't know a damn thing. So if I'm doing a test about how a drug affects...
Wait, I'm sorry.
Oh.
I did not hear anything you just said. Can you back that up?
Yeah. Hey, guys. So, chapter 8, you got one sample. Right, so there's only one sample that shows up in the equation. And you're comparing it to some known mean or some claim about a mean. But normally what we do, if I set up a drug study, we're going to have a control group, right? And we're going to have another group that gets the drug, right? So let's just say 2 groups for right now, just to make this simple. 3 would be, that's later. So we got one group that doesn't get the drug and another group that does. So they're both samples of the population, right? So then I need to compare 2 samples, not a single sample versus some known thing, right? Like some known drug versus mine. I want to compare the effects between these 2 samples. So then what's going to happen is it's going to be the exact same formula except everything's just doubled. Now there's 2 sample means because I have 2 samples. And there's going to be 2 means for each population that the samples come from. Maybe it's men and women. Maybe it's, who knows? So now in chapter 9, it would be x bar 1 minus x bar 2. Minus mu1 minus mu2. Double because you got 2 samples. Double because you got 2 possible population means, right? And the bottom, let me show you. Remember, what is sigma x bar again? What's the formula for that?
Sigma.
Beautiful. Are you guys cool? Can you see how this works also? Isn't that the same thing? Because the square root of sigma squared is sigma. So those are the same things. So now watch. Double the means, sample and population means. And then you double the sigma and n. There's 2 different samples, and I have 2 different sizes. They're going to have 2 different standard deviations. If I don't know sigma, what's going to go there? S. I love it. Whenever I don't know sigma, I use S, which means then I would be using t-scores. It's the same exact idea. So the only real difference, all the steps are the same. The only real difference is on step 4, how you calculate your z star would be using this beefed up formula, which I still argue is the exact same formula we used before. It's just got 2 means in it. Yeah.
So if we know the sigma, those 2 would be the same, but if it's S, they would be different?
No. It could be 2 different populations entirely. So for my drug example, it would be 1 population, and I just broke them up into 2 groups. So then these might be these would be the same.
And your means would be the same.
But I could have like a population of people from Italy versus population of people from the U.S. to see the dietary effects. So the standard deviations there would be most likely completely different. Yeah. Cool.
Why did you change it from sigma divided by square root of n to that?
So if I have 1 sample, I just have 1 standard deviation that I'm concerned with, right? If I have 2 samples, I have 2 standard deviations. Still effectively the same kind of setup. It's just that here I had room for 2, here I've got room for 2, so here I've got to make room for 2.
I get that part. It's just why it changes from sigma divided by the square root of n to sigma squared divided by n.
So then I'm able to do this. I can put all of this under the square root.
Oh.
The mathematical reason for why is exactly this. Because you could say, well, why wasn't it just sigma 1 over square root of n1 plus sigma? Because it wouldn't work mathematically. It's the quick answer, right? And this is the real kind of, this is the real equation, to be honest, and we just always use a simplified version. So we have to go back to the real equation and then beef it up by 2, because I've got to have room for both of my populations to be in there. So trust me, this is an overview of the idea. There's a lot of math behind it. Why is it exactly this? But I'm hoping you guys can see, I can't just have room for 1, I need room for 2, because now I'm talking about comparing 2 samples. Right? And normally our null hypothesis is that these are equal. And we're trying to show that no, they're not. So if I'm testing a drug out against some other drug, I want to show that my drug's better. So the null I'm fighting against is that they're the same. No, it's the same, dude. And I'm trying to say, no, mine's better. Mine relieves your headache faster, so that would be a one-cell test that way. You guys kind of with me? So if the null hypothesis is that these are equal, this is normally 0. Because then mu1 minus mu2 would be 0 if it's equal to each other, right? All right, cool. And then it becomes just the difference in those sample means divided by the standard deviation. So it is sort of like a z-score telling me how far apart those samples are. So if I think the women's average grade versus the men's average grade is higher or something, I would calculate the z-score. I'd say, how far apart are they? Are they far enough apart to show evidence that they are different? That sounds a lot like what we did here, except I'm talking about some given score versus my sample. Whereas this is just straight up 2 samples. How far apart are these 2 samples? Okay, that's all I want to talk about. That's bonus. You guys can, and then you got the p-hat stuff in the other section in 9. And you can imagine it's got p-hat 1, p-hat 2, same way. Doubles everything. Cool. So if you want to, you can try that out. If you don't want to, you don't have to, because it's bonus. It's not going to count against you. Okay. So what I want to do, if there's no specific questions from chapter 8, we're actually going to get into chapter 10. Appreciate you holding your groans back. That was awesome. For once. So are there any questions from chapter 8 before I move on? Poor little camera dude.
So chapter 9 is not going to be on the test?
If normally I put it on the test as a bonus. So if you do the extra credit work, you'll get extra credit for the homework if you get enough of them right, and you have a chance to get something on the test too. Yeah. Okay. So let me give you this here. Chapter 10 is the one chapter where I allow us to do the bulk of the analysis directly in our calculator. Okay. So you're finally going to have the calculator fully living up to its $100 price tag or whatever it is nowadays. Yeah.
Thank you.
It's the most popular though for some reason. All right, so first off, a disclaimer. This is not a suggestion for a project. Just want to get that on film in case you go to my dean and say, the teacher told me to get drunk. All right. And when I applied for this job, this is actually we had to take a video of one of our lectures, and this is the one I happened to be doing at the time I had to send my video over. So later I was told, yeah, we like the fact that you talked about beer. I'm like, no, your requirements are stringent. So you're like, oh great, this guy's got the job just because he's talking about beer. So this of course is a little bit silly, but it's just to get us into this idea of what correlation is, and then regression comes next. So if you did go out the night before, you had a 7 a.m. class, you had a 7 a.m. test, right? And you have a certain number of beers the night before. Now, there's a lot of variables involved here. You could either not know a damn thing, no matter if you're sober or stone drunk, right? So, where on this picture, which one of these pictures is more realistic?
The first one.
Yeah, what do you think? It's not that one. I really want you to understand. That's more realistic. Who is this dude here? Did he have a lot of beers?
No.
No. Well, how did he do on the test?
Not well.
So that's the guy that no matter how sober he was, he would do bad, right? Could be a she, I don't know. I'm not trying to say anything. Who's the other kind of outlier, the extreme person? There's one other person.
In the corner.
This guy. This is the person that
Drinks a lot.
probably drank the most and almost got one of the highest grades, right? So that requires somebody who's able to hold their liquor, and also they know the stuff, or else there's some weird, the more beer you drink, the smarter you get. Again, this is not something like my friend Scott would get better and better at pool as he drank more and more, and I would just basically stay the same sucky level no matter how much I drank. I try to keep him sober for playing for money. So if I took those two out, it just kind of makes it a little more pronounced. Now, this is not actual data. I just want to make this clear. I did not ask this class to do this. But even if I didn't take those out, is there like a line you could draw that kind of represents where this is moving?
Yes.
Yes. So you can kind of, there's enough in the middle to kind of tell me it's kind of going down a bit. It's not going to be it's going to be a strong relationship. Meaning, can you say for sure that if you have more beers, you're going to have a lower grade? No, I can't say for sure, but there seems to be some kind of a bit of a trend. You would expect somebody to have a lower grade possibly than they could have if they come in the next morning with a bit of a hangover after, like 4 beers the night before, right? Some people have 4 beers that morning and they come in, they're fine. I don't know. This is happening. And the second, of course, is not nearly as realistic, but it's definitely going to be a lot stronger. If I drew a line on there, so this line I would draw would be something like that. Maybe a little bit lower. I kind of missed it. But that is a graphical average of all the points. That line I just drew. So this one is a lot easier to see where it would be. It's going to be right down the center. It's very strong. Those points are really tight to that line. So I can make a prediction pretty easily. Right? Now, of course, the line only is true for so long. You're not going to say, man, if I had 6 beers, you get a negative test grade. Holy crap. No, right? Unless you ran me over the way in. I might get a negative test grade. You guys kind of with me? Does this sort of make some sense here? What we're talking about? So we're talking about the effect that one thing has on the other. Now, of course, behind this whole thing is something we've talked about since chapter 1. If I see a correlation, does that mean that one thing causes the other thing? No. Somebody could be drinking a lot because they're upset that they're having such bad grading statistics, right? So they're probably going to have another bad grade on the next test. So there could be, who knows which way the effect is. But all chapter 10 does is say, is there some kind of relationship? So an example I gave my pre-calculus class, because we talk about parametric equations, which is where there's a variable behind the scenes. So if the temperature goes up, what do you think is going to happen with sales of like lemonade? They're going to go. What about sales of ice cream? So somebody could go, why would selling more lemonade make more ice cream sell? And of course, this guy's a doofus. So behind both of those, so I would see, if I plotted out lemonade sales versus ice cream sales, I would definitely see a nice tight correlation there, right? But what really is true is they're not affecting each other, they're both being affected by temperature in this case. Does that kind of make sense? So that's one way you could have why just seeing a graph like this does not prove that the number of beers you have affects your grade. There could be something behind the scenes like your depression about having a bad grade. I don't know. Okay. So here's just one more example, a little bit more. This one I would highly recommend you try out. Hours studied versus the grade you make. Right. So which one's more realistic?
The one on the
this is a little more realistic. Right. And so this person, for example, they studied a lot, but they still didn't do very well. And what they normally tells me is they're not sure what studying means. They're doing something, but it's not really studying. You just are doing something for 7 hours, but it's not really what you should be doing. And whereas this person is a person that most people kind of hate.
Yeah.
They come to class only when there's a test. They never open the book, and yet they crank out the A's, right? And you're like, who the hell are you? Just remind yourself they probably took the class twice already, and that's why they're doing so well. So again, would you call this relationship here a positive or negative relationship?
Yeah, positive.
Totally. All right, so that makes complete sense. The slope is positive. As hours studied increases, it looks like grades increase. On the other one, as beers increased, it looked like grades decreased. So that's why it's a negative correlation. Whoa, neat. Okay. So it would be great if there was some way to find a number that would enable us to quickly talk about how strong the relationship is, and there totally is. And it's sort of like, I think of it almost like a two-dimensional standard deviation. The further the points are away from it, the score does something. The closer the dots are to the line, the score does a certain thing. So what happens here is, if I had perfect negative correlation, which would mean as this goes up, this goes down in a perfect straight line. Pretend like that's perfect. There you go, Jeff. Sort of. So that would be perfect negative correlation. As x goes up by 1, y goes down by 1, or something like that. Right? That slope is consistent all the way through. It goes through all the points. That would be an r. That would be this value that we calculate is given the letter r, and that stands for like it's called two different things: correlation coefficient or Pearson product. So of course they gave it the letter R. That only makes sense. No, not really. In this case, R would be -1. So incredibly enough for perfect positive, if it went lockstep up, straight line, that would be R equals to 1. I love it. So those are the extremes. R could be anywhere between 1 and -1. So I would guess, for example, what would be a good guess for this? What would you think R would be there? It would be close to what? Really close to -1. It's really pretty tight. It's not perfect. So like -0.9 or something. So that I would say a good guess for this would be about -0.9. A good guess for this, I don't know.
Maybe.
That was a lot harder. Yeah, maybe I heard a -0.5. That sounds about maybe good. Well, I'm actually going to do that. I have the data behind the picture on the other side. Okay, so R could be between -1 and 1. We talked about what the extreme values mean. As value of 0 means, I got to be careful. We only talk about linear correlation. Now there was a problem in one of the books where you had as the temperature went down or up, or energy use increased, but in the middle it was low, so it was like, that's not linear, but there is a correlation that's obviously parabolic, right, quadratic. So you could have dots that would be fit by a cubic or something. We're only going to talk about linear correlation, thank God, right? But you can have logarithmic correlation that follows like a natural log. You can have power that follows like 3 to the x power. You can have all these different correlations. We're only going to talk about linear. So if we get a 0, it means it has no linear correlation. It might have something else, but it's got no linear correlation.
They could be the same, right?
How do you mean?
Like, never mind.
So I could have, that's right, something on the back of that. I could have a situation like the temperature and the energy use, where I have dots that sort of like this, so they fit really close to a parabola. So the R for us, we would get 0 for that most likely, because there is no straight line that would go through that data. It's got to be curved. So I'd have to do a test using a quadratic, using an x squared kind of thing. We're only going to use like mx plus b. So this would be 0 for us. What about this? What if I saw something like this? This is a nice straight line. What kind of correlation does that have? 0 correlation, exactly. So if x is how far I can jump, and y is how tall the tree is right there, I don't care how high I jump, is the tree suddenly going to become a different height? No. So they obviously are not correlated. X is changing. Y doesn't give a shit. So that means there's no correlation. Don't think that, oh, it's a nice straight line. One of them doesn't care if the other one's changing. So, of course, the other extreme there would be vertical line. That would be no correlation also. Cool. I like it. I like it. All right. So let's try one of these. Let's just go for it. Let's try that Beers and grades problem. I'll let you do that. See how it comes out. So let me show you how to do this. How many variables do we have here? Now, how many values? How many variables?
1.
2. I've got number of beers and grades, right? So I've got 2 variables here. So I want to put L1 as beers, L2 as grades. So you guys go ahead and get started. If you want to borrow a calculator right there. I've got to wait for my computer to come up.
Oh, yeah. Oh, man.
Alright, so you guys got that handout. Try to finish up. You think you ever want to sort anything with this? Hell no, man, because the X and the Y have to stay together. If you ever sort the list, you're always everything's going to have a really nice correlation because you're forcing them to kind of line up. It's no good. Don't do that. All right. Hopefully there's 14 things. So what I normally do is somewhere I stop and I say, okay, 74 goes with 3. Cool. Okay, thank God. All right, so once you get it all in here, if you're using your own calculator, what we're about to do never has to be changed. It's always going to be there for you. Does that kind of make sense? You don't have to do what we're about to do every single time. We're going to set it up so that it will always graph our statistical, our data points. And we're also going to set it up so it's always going to show me the value of R. All right, so here's what we do. First thing is, let's try to get a scatter plot of this bad boy. Let's see what this thing looks like, and make sure it looks like what it's supposed to on the other side of this paper. So if you go to second y equals, see where it says stat plot?
Yeah.
Coolness. So make sure that we're going to do, it doesn't really matter which one you do, just make sure that only one of them is going to be turned on. So if they're all turned on, just hit number 4. Maybe that's a good idea. Just hit number 4, enter. So we all start with everything turned off. It's a good idea. So now if you come back to second y equals, they should all be turned off. Cool. So let's all go into number 1, hit enter on top of 1 here.
How do you get there? You put
Second y equals? Yeah. And this is this whole, it's on that calculator Bible sheet I gave you way earlier, but it's also on the back of this again. Then hit number 1. And you want, so turn it on. So on top of on, just hit enter. So now it should be highlighted. Good. And look at your evil teacher not telling you about histogram and stuff. It's too bad. So this first one. So this first one, we want the scatter plot. So make sure that's highlighted. Scatter plot. And then you can control where your data is. Of course, X's are in L1, Y's are in L2. So make sure it says that. How are we doing so far? And then you get to pick, are you a square, are you positive, are you a speck of dust in the cosmos? I, of course, am a math teacher, so I always pick the square. The speck of dust thing, you guys hear about the spacecraft landing on the comet today?
Yeah.
Isn't that weird? Of course, Google had it up. I'm like, oh, good, now everybody knows, thank God. Because it's just so kick-ass. And the last thing I heard was the little things that are supposed to hold on to the comet didn't work. So I'm not sure what's going on with it. I had this image in my mind of it just kind of rolling around the surface of that would suck. The instruments probably wouldn't handle that too well. But if you didn't know about that, just go to Google and you just click on the image and you can get information about it. Okay, so once you picked all this, if you hit graph, you probably get something really sucky. I got nothing, right? So what you always do, the minute you put new data in, you go to zoom. Exactly. So if you go to number 9, it says zoom stat. Zoom stat. And so that's going to zoom in on my statistical data points. That's crazy. So you get that. And if you compare that, I think I got pretty close. Because I drew this and then I tried to make data that sort of looked like this. And I got pretty close. Okay. So just so you really understand this, whenever we have a test or a quiz involving this, you will have to come up and show me a couple of things. One thing is this, but also you're going to have to show me the line that best fit on top of it. So we're going to talk about how to get that. All right, so far this is just to get this the dot plots or the scatter plot, so I can see if it looks like there's any trend. And it looks like there's a little bit of a trend, like we knew. Yeah.
I missed what you did from the plot 1, plot 2, plot 3, where you were talking about the little square guy. What you did to get to that page.
So you're in here, right?
Yes.
Now just hit zoom.
Okay.
9.
Oh.
I hit zoom 9, I got an error.
What's it say? Dim mismatch? Or does it say syntax?
Syntax.
All right. So this is also on that, your calculator Bible thing. If you get syntax error, normally it's y equals. Normally there's something weird in here. So hit the y equals and make sure that all these are clear.
Yeah.
All right, cool. Now hit zoom 9, see what happens. Matt, are you okay?
Yeah.
Mine didn't go to that at all. So no.
Oh, so
So long
Yeah.
today. Because it's Monday?
It feels like Monday.
It's because of the hypothesis testing.
Everybody else all right? What's up? So you went to here. You want scatter?
Yeah, I'm already. I'm living. I live in
It's on. Enter for the scatter point.
Everybody.
Now hit zoom 9. Cool. All right.
More than anybody I know.
Everybody else all right?
I don't need to.
All right. So let's see. Depending on what your calculator's been used for before today, this next thing we do is going to be different for some of us, but then I'm going to do one thing that's going to make everybody the same. Here we go. So we want to go back to stat. You know, at some point you're just going to hit that stat button. And now I want to go to calc. And now, where do you think I want to go, considering
4.
2
Line right.
Yeah, you might think 2 var stats, and that's if I was making you do the formula for this. But we're going to go straight to number 4. I want to get the regression line. I want to get the line of best fit. That's one thing I want. And it also gives me the R value at the same time. It gives me the strength of the fit. So if you go to number 4, what's really funny to me, by the way, is there's a number 8 where, look what they do. It's A plus BX versus AX plus B. Ooh. I have no idea why they did that. But just use number 4. So if you hit number 4, enter. How many of you guys, let me do that again. So go to stat, calc, no see crap. Number 4, and it defaults to list 1 and list 2. So you have to tell it if you have it in different lists. Enter. How many guys just get those 3 things? And the rest of you get some more stuff, right? Some of you guys get R squared and R.
I only got the equation.
Oh, you didn't even get A and B?
No, it just...
Hit enter.
Oh.
Okay, cool. All right, so here's how, because we need to know how strong this is. So we do know right now, what's the line of best fit?
Y equals negative 2 point.
Where am I facing here? Let's point you in a useful direction. Yeah, negative 2.5 4x plus
89.
Okay, guys. So that is the line of best fit. Very often you see a little hat on that dude even. Because it's not going to be the real output. It's going to be the predicted output. Because this line doesn't have to go through any data points. No. So it's not going to necessarily give you the actual Y value. It's going to give you the predicted Y value. So what's going to tell me I trust this thing is how strong the relationship is, how tight the points are. If they're not very tight to the line, I'm not going to trust this line. I'm not going to even use it if it's not strong enough. So let's first calculate R, and then I'll tell you how to figure out what's strong enough, because 0.9 sounds pretty strong. But where is it? 0.6, is that still okay? I don't know. And what do you think it depends on?
Slope.
What's the major thing in statistics that if I do this, I'm more sure about what I found? Sample size. Right? The larger the sample, the smaller your R value could be to show evidence of correlation. Okay, shit. So let's first figure out how to get the freaking correlation thing to show up, the R value. And I know it's going to at least be what for this one? What's the one thing I know about R? Maybe 2 things.
Negative?
I know it's not going to, I know it's going to be negative. I know it's not going to be close to -1, really. It's kind of weak, right? It wasn't really strong. Our guess somebody had was -0.5. From where I think it was you. Okay. So here's what you do if you don't have the R squared and the R showing up. Here's what you do. You ready? Hit second, 0. This is a catalog of every damn thing your calculator can do. It's really kind of neat. See how the little A is on? So now if I hit see where the D button is right here where it says X to the -1? See the little green D? Or for you it might be, I don't know. Is it green? Yeah.
Yeah.
So hit that button, the X to the -1 button, go to the D part of the list. And again, this is not something you have to do every time. This is something you have to do once. If you're using your own calculator. Go down to where it says diagnostic on. See there it says diagnostic on? And again, this is all on the sheet. On the other side, it's got this is on there. If you have to do this later yourself. Hit enter. Enter. Very anticlimactic. Done. And you're looking around like, what happened, man? So now if I go back to stat calc number 4, I'm going to get r squared r also. Right? I'm going to see it's even a little weaker than we thought. Our guess was -0.5. It's actually just -0.33. Pretty weak correlation if there wasn't. Okay, maybe. So let me show you. On a test or a quiz, I will tell you the cutoff that if it gets above that, it's correlation. If it doesn't, it's not correlation. Right? I will tell you. But let me show you right now where it is. It says this on the handout. It's table A5 on page 588 in the new book, page 608 in the old book.
What is that showing us?
See?
What is that showing us?
I'll show you.
Oh.
It's showing you this. Oh. Alright. So please, dear God, understand that this is the only time we are almost going to see this. Look at that autofocus feature. It's awesome. That statistics are so beautiful, John. Alright, but if you got the book open, you only have to look at this once, because I'm going to give you the value. But you can see, based on the sample size, the requirements for R. Hello, are we still blurry? That is so funny, man.
Try to zoom it out.
That's great. All right. So let's see. For us, I think it was 14 data points, right? So I wouldn't say 28. I'd say 14 data points. Kind of with it. So at 14, it requires either 0.532 or 0.661, depending on, holy shit, your level of significance you want to use. Now, some of us are thinking, oh God, no, there's not going to be any. There could be hypothesis tests related to correlation, but I'm not going to make that happen. I'm just going to tell you which one I want you to use. How we do? So no matter which one, what was our R? Yeah, the negative really doesn't matter for this table, right? Sort of like the t-score table. So it was 0.33. It wouldn't pass either one of those tests, right? It's required to be 0.53 or 0.66 or better. Because closer to 1 is better, it's stronger, right? We're at 0.33. We don't even have evidence to say that there's any correlation at all. Cool, so it was just too spread out. So I'd have to take a larger sample to show that there's evidence, or a larger sample to show, yeah, it actually is getting closer and closer to 0, maybe. Maybe it'd be evidence that there is no correlation. How are we doing so far? So I'm going to tell you on a test, I'll say, do a correlation study on this, get R, get your line of best fit, use R greater than 0.44 or something to show evidence for correlation. Okay, cool. So if I said 0.44 and you got 0.93, what could you say about the correlation? It's strong and it's positive. Sweet. So when I say interpret what R is, so I think I say that on this handout. What do we get so far? We got, what do you get for R? Negative 0.34, something like that, right? I think these are math symbols in some language. Is this a strong correlation? Oh, shoot, yeah, the focus just doesn't want to get in close. Is this a strong correlation? No, it's not even any correlation. No correlation. What kind of correlation is it? It's none. If there was a correlation, it would be very weak negative correlation. But it doesn't even have evidence that there is correlation.
Where's the cutoff for correlation?
So
Did you say it was 0.5?
yeah, because we had a sample size of 14.
Oh, okay.
Oh, I didn't put it on there. I just was going to show you the table. But on a test or something, I would just put the number on to the test.
Okay.
And then Y we got up there on the chart. Now, I want to show you this. If you go back to the your calculator, this is what you got to come up and show me on the test. Go to Y equals, and now you can just put the line of best fit in. Here's your X button right there, right? So negative 2.54X plus 89.83. Of course, if you left the X out, it would just plot a number, so you just get a horizontal line. Yes, sir?
Where's the X button?
Oh, it's right here.
Oh, got it.
So yes, your all-purpose variable button.
Okay.
In a graph,
That's awesome.
what kind of error do you get? Go back to Y equals, you probably put a minus sign instead of a negative.
How do you put in a negative?
So again, there's a minus sign and there's a negative sign.
Oh.
They did that, they didn't have to do it, they just did that just to screw students over. That's the actual story. No, it's not. Now what I want you guys to do, you knew this is coming, I want you to do the other set of data, do the whole thing. For the grade, for the study. If you did already, just sit there and stare at your favorite wall for a while.
So we had to show you this test.
On a test, you would come up to the desk and show me this.
So just with our calculator.
Yep, exactly.
So what do you do once you put in the equation?
Sir? Graph. Hit the graph button.
So there would only be like one problem like this on a test or something? Or we have
Yes,
to get a multiple
there would only be
choice?
one
Okay.
of these. Yeah. This takes a little while, so. So, good, yes, so if I just said interpret R, you would say it's a strong positive correlation. But I kind of like broke it up into two parts. This is not the actual Y value. We'll do that. I don't trust that line. Why do I not trust that line? It's a little shifter.
Because it's like stairs.
Because the points are all far away from it.
What tells me how strong the fit was? R. And R was only, it didn't even show enough for correlation. I don't trust that line at all. So my best guess for Y is the average Y. If I trust the line, I can do better than the average. I can actually plug a value in for X to predict what Y would be. And that's why it's got a little hat on it. Because it wouldn't be the real Y, it would be a predicted Y. Cool. Yeah.
Are we supposed to be finishing this paper up?
Yeah.
Oh, yes, that's what I was talking about. R.74. How many data points? It's more than 4. So it's going to be even easier to pass than the 0.5 one we were just looking at. So that's definitely enough evidence for correlation. So would I trust it? Yes, because it's strong enough. The points are close enough to the line to trust it to make predictions.
What?
Because the more data points there are, the lower R can be.
Oh. Why did I No, I got 7.5.
So the mismatch means you have two different size lists. They don't end at the same time. Oh, L1 is
What point? The second stack.
whatever you say. So here's what's cool. You just kind of make that.
Oh, okay. So select that one.
And I shifted everything. I like the redo default.
That you grab.
Yeah.
It's like
Make sure it's on, so you can actually see it.
just like tingles to the table. It's like, oh my god, this is like really funny.
Fall over is probably.
Yeah, it's A plus jersey.
So I think.
For this one, you completed that one on the board. Okay.
Oh, eventually it took me
No, we did it wrong.
It's something four. It's,
Four.
yeah, it's stat four.
Yeah.
Not stat. I told you that.
So you did. Why are you lying?
I said stat four. Next.
Oh, that's
Oh, I see.
Read the Bible.
So stat.
You got this one.
Count.
And then.
Go down to number
Yeah, that's right. So you got the one that's got a little bit extra. I just forget to have these updated. They've updated software. So the free, you could have another list.
You did 9 and 7.
1, 2, 3, 4, 8.
Oh, wait.
I just used that one, I got 17.
So we don't want to put any. We don't want to help.
Yeah, I got 4. 7, 4.
I got 8, 3, 7, 6, 6, 8.
Big white one?
Wow.
Yeah.
174.
Yeah.
You have to change the Y equals though.
Because if you don't put an S, it's a number.
Is it parabola or
Parabola.
Yeah, it's just gonna
What are we
be-
talking about?
There you go. So it's gonna be even a little
dark
more.
out.
Oh, it's asking you change the Y equals.
Yeah. Feels like I should be at home right now.
It's like dark at 5:30. Feels like 8 or 10.
And I have a class after this too.
It's like 5:30. Yeah, wait till summer where it's like.
There's my
until like
phone.
7:30.
I did 2 and 7.
We're barely in fall and you're I can't wait till summer.
I know, really. I just hate the time change.
I've been like that since last month. Literally, I've been counting down. 7 months till May. Literally, I've been like that.
You don't like it?
Huh?
You don't like it?
The winter is cool and I appreciate it, and whenever it comes, I enjoy it. But I always miss the summer. I mean, I was born and raised here, so it's like, I don't know. I guess you just get so used to it. I don't know. I love the heat.
Yeah, 7 minutes.
Not very.
So is that a strong correlation?
I want to move somewhere where it rains a lot, though.
No, you don't.
I do.
I lived in Seattle, no, you don't.
I do. It's beautiful. I mean, besides the fact that it rains every day and it's depressing.
It doesn't rain every day. It just rains for 33 to 48 days straight at a time.
Produce go.
Yeah.
You have like a day of break.
Oh, okay, so yes, it is.
Well, let me put it in.
It's alright.
I still want to live somewhere where it rains a lot, just because I want to experience something different.
You know where's nice where it rains? Hawaii.
Hawaii is awesome.
Yeah. When it rains, like we went a few summers ago to Hawaii, and it's like you're just walking on it. It was in the summer, so you're just walking on the street and it's nice and warm, and it just starts raining out of nowhere.
I
And it's
hate
nice.
that though.
No, but it's like you enjoy it because it feels warm, but it's raining. So you just keep walking, and like nothing's happening. And it's not even hard rain; it's just light rain. It's nice.
I've never enjoyed that, but maybe it's because I've like, is it, I don't know. I just don't enjoy the humidity. The humidity's never felt good to me. It feels like it's worse than heat. Do you like humidity?
I like very moderate temperatures. Like it has to be an even. So like here, when it gets really hot, I don't like it, and when it gets really cold, I don't like it. Somewhere in the 80s is fine.
That's still pretty high though. Like compared to, like if you said that to someone from a different part of the world, they'd be like, that's so hot.
But for here, it's kind of normal.
Yeah, for here it is.
All right, guys. Let's see if I put this in here right. So one thing I want to do right off the bat when I put brand new data in, go to y equals and clear that out. So now if I hit graph, why do I see that? Because my window's all freaky. I got to go to zoom. Zoom is what makes the window move to the right place. So if I hit zoom 9, there's my scatter plot. Cool. So this is not good enough to show me when you're taking a test. You got to show me that line too. So how do I calculate that? Stat. Calc. Number 4, enter. Cool. And if anybody looked at the table, I can't remember how many data points this has. 19. Thank you. So the cutoff would be 0.456. The cutoff would be 0.456. So did we find evidence of correlation?
Yeah.
Yes, that kicked that ass, right? It went way past that. So, but this isn't like 0.8, 0.9. So I would accept you could say decently strong, not very strong, but not weak. You know, something like that. It's not like strong. It's strong enough, sure. Decently strong, moderately strong. It's got a hint of strength. Whatever. with the floral aftertone. I don't know. I don't drink wine, if that wasn't clear. So if we go now, what can I get from this? What else can I get from this?
Your equation.
So I've got my R, which is 0.738 roughly. I got my equation, which is going to be 0.66x. Now, of course, in statistics, we use the letter A. In algebra, you use the letter, what is that really? A, what is that from algebra? Slope. So that would be M. So, of course, statistics just had to be different. Right? Don't worry.
How far do you normally want to take your R out?
I freaking love algebra.
Couple of
Just a couple.
Yeah. Plus.
I love algebra. It's awesome. I
It's
hate
like the
it.
simplest form of math.
Yeah, I hate it. I hate it freaking.
So now if I put that.
No, calc is awesome. Calc is bomb big.
I like to hear that. It's good. But if I put that into y equals, if we put that equation in there, this will be 0.66 x plus 70.97. Thanks. Pickens the acid. Yeah, so it actually goes through 1 point perfectly. Yeah. But it's just a graphical average of all the points' locations. And what it actually does mathematically, it tries to minimize the square of the distance from every point to the line. So that's the math that's kind of like behind this. So that's enough for today. Next time we'll focus on doing a few more of these, and then we'll see where everybody is with hypothesis tests. Yeah, do you trust it? Yeah, we found evidence. It was decently strong. Yeah, I would trust the line.
So we have a